Okay, our last conic section we're going to look at is what's called a hyperbola. Now, a hyperbola is similar in its definition to an ellipse, where you have the two distance from the two set points, but instead of being the sum, it is the difference. So a hyperbola is the set of points whose difference in distance, so we're subtracting instead of adding, from two set points is constant. And those 2 points are again called foci, but this number is always the same. So this is the formal definition. It's all the points who, if I take the distance from these 2 points and subtract them, I get the same number. So what hyperbolas kind of look like, they have a kind of a neat kind of shape. They are these kind of opposing kind of parabolas that look like this. So this is the actual part that is the hyperbola, is these kind of curved things throughout the different plane. They can also go up and down. They could go up and they could go down. These just happen to go left and right, but they certainly could go this direction and this direction. But there's always 2 of them, and they always oppose each other. Couple neat things we have here. Some different things and points. A lot of them are very similar to the ellipse. So what you can see is there is a vertex where both of the parts of the hyperbola intersect what's called the transverse axis. Now the transverse axis is where all the good stuff happens. It is kind of similar, if you remember, to the ellipse. It was the major axis. Everything happened on the major axis, and this one we call it the transverse axis. So we have these 2 vertices, which is where the hyperbola intersects the transverse axis. We also have 2 foci, a focus on either side, which is inside the hyperbola. It's inside the curves. We obviously have a center where everything kind of starts here. And the only thing that's kind of different is we have these slanted asymptotes. And these are just really lines that help us to see where the hyperbola is going. So these are just lines, these are just mx plus b lines that kind of where the graph approaches. So what you'll see is this hyperbola, say this side, is going to get closer and closer and closer to that line, but it's never going to touch that line. It's just going to get closer and closer and closer and closer. So the equation of a hyperbola, very similar to that of an ellipse. What you can see here is the equation of a hyperbola is x squared over a squared minus y squared over b squared equals 1. So what you can see the difference is we have a minus sign. And the transverse axis in this case is the x-axis. In an ellipse, the biggest axis or the major axis was always which number was bigger on the bottom. But you can notice in both of these things, one with the x and one with the y, A and B are in the same location. How we determine what the transverse axis is what variable comes first. So it becomes the x comes first before the subtraction sign. The transverse axis is along the x-axis. If you look down here, we have the y first, so the transverse axis will go along the y-axis. So if it's on the x-axis, the hyperbola will open left and right, because it's going to intersect basically the x-axis, something like this. If the transverse axis is along the y-axis, the hyperbola will open up and down. So the important thing is we have this A, B, and C. And again, very important things to recognize in this problem. A is the distance from the center to the vertex. Okay, that's kind of very similar to as was an ellipse. C is the distance from the center to the foci. B doesn't have a really good definition, like B in an ellipse was center to covertice. In a hyperbola, it's just kind of part of these asymptotes down here. So each of the hyperbolas will have a pair of asymptotes, and if it's the transverse axis, it's y equals plus or minus b over ax. Those will basically, that's going to give us our two kind of dashed lines that our hyperbola is going to approach. So it's just basically those things that make the cross, and then our hyperbola will go inside. We also have a really neat relation. It says b squared equals c squared minus a squared. So it's the exact same as an ellipse, except for a and c are switched. Everything is very similar for the hyperbola centered at the origin, with the transverse axis along the y-axis. Like I said, only difference is y goes first. That makes it's going to go up and down because the transverse axis will go up and down. Everything else is the same. We have our distance from center to vertex. We have c being the distance from the center to the foci. Same relation. But if you look at the asymptotes, they're a little different. Instead of being b over a, in this case, they are a over b. So right here in these two equations really gives you everything you need to know to be able to deal with these hyperbolas. So let's look at an example. Find the equation of a hyperbola with a center at the origin, one foci at 8, and one vertex at 4, 0. Also state the equations of the asymptotes. Okay? So I'm going to make a little sketch here and kind of see what we have going on. So we have our center right in the middle. That's good. We have one foci at 8, 0. So that's way out here. That's a foci out here at 8, 0. And we have a vertex at 4, 0. So I know the hyperbola, since that's got the vertex, it's got to go through that vertex. So the hyperbola looks something like this. So the transverse axis is going to be the x-axis because anything that opens left-right has a transverse axis of x. So we're really going to be talking about the kind of problems that look like this first box, where it has the transverse along the x. So I know my equation, because that's what I'm trying to figure out, is going to be x squared over something minus y squared over something equals 1. Because we know x coming first will make it have a transverse axis of x. So really what I have to do is very similar to an ellipse. I'll try to figure out what a, b, and c are. Now a is the distance from the center to the vertex. So the center of the vertex, which is 0, 0 to 4, 0, would be 4. And c is the center from the distance from the center to the foci, so that's 0 to 8, which would be 8. We don't know b. What we do know is we know a squared is going to go under the x, and the b squared is going to go under the y. So we know a squared, that's 4 squared, that's going to be 16. Easy enough. We don't know b, but we do know a. So we'll use our little relation, b squared equals c squared minus a squared. So b squared is going to equal 8 squared minus 4 squared. That's 64 minus 16, which is 48. So b squared is 48. So if I want to find what b is, I just take the square root. So b is the square root of 48. But what I really want in our problem is I want b squared, because it's y squared over b squared, so this would just be 48. So there is the equation of my hyperbola. So if I were to graph this on, say, Desmos, this would pass through that point on the vertex. It would have that foci at focus, although we don't see the focus, just as in the other problems. It also one of the equations of the asymptotes, but if you look up here, the asymptote equations are just y equals plus or minus b over a. That's why it's important to have these notes handy, because you can know exactly what the asymptote equations are. So it's b over a. So our asymptotes are just y equals plus or minus b square root of 48 over a with an x. So this is the equation of my hyperbola, and these are the equations of my asymptotes. Okay, let's look at graphing a couple hyperbolas. So this one, we have 4y squared minus x squared equals 16. Well, the problem with this one is it's not equal to 1, so just like what we did for an ellipse, we'll divide everything out by 16. So 4 over 16 is 1/4, so I can rewrite this ellipse as y squared over 4 minus x squared over 16 equals 1. So I see that the y comes before the x, so the transverse axis is going to be the y-axis. So that means my foci and my vertices all go here, and that means that my hyperbola will open up and down. So if I look at this problem, I know a is 2, because a squared always comes first, and this is b squared. So a equals 2, b will equal 4, and c we don't know. Now a is the distance from the center to the vertices, so since the center is going to be at 0, 0, because there's no shifts, I can go up 2 and down 2 to get my two vertices. So I have a vertice at 0, 2, and 0, negative 2. B really is part of the asymptotes, which I don't know yet. C I don't know, which is distance from center to foci, but I can figure it out because we know in a hyperbola, b squared equals c squared minus a squared. So b squared, which is 16, equals c squared minus a squared. 2 squared is 4. So if I add 4 to both sides, I get 20. 20 equals c squared. Take the square root, c is equal to the square root of 20. Now the square root of 20 is somewhere between 4 and 5. So I know I have a focus up here, and I have a focus down here of some sort. Now if I remember the asymptotes, because it wants the asymptotes for a hyperbola opening up and down, y equals plus or minus a over bx. So since a is 2 and b is 4, this is y equals plus or minus 2 over 4x, but 2 over 4 is simply 1/2 x. So if I start at the origin, they always start at the center, go up 1 over 2, this would be a positive asymptote because that's up 1 over 2 and that's my slope. And then if I go down 1 over 2, I'd have one that goes like this. So the real purpose of these asymptotes is it kind of gives me an idea how my ellipse will, or my hyperbola, pardon me, will be spread out. So it looks like this. So those two opposing black curves would be my hyperbola. I've got my foci, I've got my vertices labeled. I made the asymptotes because here are my asymptote equations. And again, I just remember because I remember from the previous page where we had those formulas if it had a transverse axis of y. Down here you can see what it looks like on Desmos, very similar. It has the nice going through 2 and negative 2. If I were to draw a slope in here, up 1 over 2, then this would be my asymptote, and you can see how it gets really close to that hyperbola. Okay, so this hyperbola is already in standard form because it already has the 1. So the transverse axis is going to be the x-axis because you can see it comes first. Okay? So everything good is going to be happening on the x-axis, so this hyperbola will open left and right. So again, I know A and B from the equation, and I can find C. So A is going to be the square root of this number, so it's the square root of 2. B is going to be the square root of this number, so the square root of 4 is just 2. C I don't know, but I'll be able to find it. So for C, again, I know B squared equals C squared minus A squared. Remember that for hyperbolas. It's the opposite of an ellipse. So B squared is 4 equals C squared minus the square root of 2 squared, but the square root of 2 squared is just 2. So I can add 2, oops, getting ahead of myself, add 2 to both sides, and I'll get 6 equals C squared. And so when I take the square root, C is equal to the square root of 6. Again, our center is at 0, 0 because there are no shifts. So I'll put my center at the origin. Now the distance to my vertices is square root of 2, which is about 1.41. So it's somewhere, if I zoom in a little closer, it's going to be somewhere between 1 and 2. So there is a vertice, and there is a vertice. About 1.4 away from the center. Okay. B is part of the asymptotes, which I don't really know yet. So C is the square root of 6. Square root of 6 is about around 2.4-ish. So about 2.4 away, I get my foci. So I have a focus there, and I have a focus there. Now the only thing I have to really figure out is how wide my hyperbola is, so I can make the asymptotes. Since the transverse axis is the x, if I go back and look at the asymptote equations for that, it's y equals plus or minus b over ax. So it's always b over a or a over b, but it's important to remember which one goes where. So y equals plus or minus b, which is 2, divided by a, which is the square root of 2x. So just to make it a little easier on myself, I'm going to put 2 divided by the square root of 2 in my calculator, and that is going to give me 1.4x-ish. So I can think of this slope as 1.4 over 1. So those are my asymptotes, either one. So if I go up 1.4 and over 1, I have something that looks like this. So I have an asymptote that looks like this. If I go down 1.41 and over 1, I have an asymptote that looks something like this. And so my hyperbola will go through the vertice and kind of get close to those asymptotes. So kind of like this. Through those vertices, close to the asymptotes. So something like that. So that green kind of curve would be my hyperbola. You can see below here is what Desmos graphed it as. So you can see the opposing curves. You can see the vertices here around 1.41, or which was the square root of 2. So very similar to what we got. Okay, now we're going to look at some ellipses that are not centered at the origin. They're centered at some point hk. So just like we did with the other ones, we'll just subtract or add h and k to x and y. So instead of x squared and y squared, we'll have x minus or plus h and y plus or minus k for these problems. So I want to find the equation first of a hyperbola has a center of 4, 8. So that's up here, right here, pardon me. 4, 8. It has a foci at 4, negative 2, which is way down here, and a vertex at 4, 10. I had to correct that, so I crossed it out here, but it should be correct on your notes. So here's my center, here's my vertex, and here's one of my focus. So I can see that the vertices are on the y-axis, so somehow this hyperbola will go up and down, something like this. Okay. So when I'm looking at my equation that I'm trying to form, I know the y will come first because it has a transverse axis on the y. Now my center is 4, 8, so I'll simply say x minus 4 and y minus 8, because the center is 4, 8, so I want the opposite of 4 in with x and the opposite of 8 in with y. Now I have to figure out what A and B are, and then I'm really done with this problem because I have A squared on the bottom of the first one and B squared on the bottom of the second one. Now A is the distance from the center to the vertex, so how far is it from 4,8 to 410? Well, that would just be 2 units. So 2 squared would be 4, so now I've kind of got that. The other thing we have is we have the center to the focus, which is 8 to negative 2, which is 10 units. But that's C, that's not B. In the equation, I want A squared and I want B squared, so I have to figure out what B squared is. But if you recall, we have that same relation we've used quite a few times. B squared equals C squared minus A squared. So B squared will equal 100, because 10 times 10, minus 4, 2 times 2. So B squared equals 96. So B would equal the square root of 96. But if you remember, we really want B squared under this one, so I'm really going to put 96 there. So this is the equation of a hyperbola that has those certain points in it. So again, it looks very similar to our other hyperbola. We're just moving the center by moving the x and moving the y. Okay, let's look at our last problem. This is about graphing a problem. So what I want to do is I want to first tell what is the center. I want to know what's the transverse axis. And then I want to know what is the A, B, and C. And then I'll find my asymptote. So everything really similar. So the center, well, the transverse axis is x because you can see the x comes first. So that means this is going to be a left-right hyperbola. The center is going to be the opposite of x, so it's x plus 1, so it's minus 1, and y minus 3, so it's positive 3. You always take the opposites, just like circles, just like parabolas, just like ellipses, always the same. So I have a center at negative 1, 3. So that would be here. There's my center. Now, this, remember, is a squared, and this is b squared. So since a squared is 4, a is going to be 2. Since b squared is 16, b is going to be 4, because we're just taking the square root of those. So if I want to find c, again, b squared equals c squared minus a squared. So b squared is 16, c squared minus 2 squared, which is 4. So I think we actually had this one in an earlier problem. So I add 4, c squared equals 20, so c equals the square root of 20. So when I'm graphing my hyperbola, I know I'm going to go in the x direction, so you're going to go left and right from my center, 2 units to get my vertices. So if I go 2 units to the right, there's a vertice there. So if I want to write what that ordered pair is, the vertices, that would be 1, 3. And if I go 2 in the other direction for my other vertex, that's going to be at negative 3, 3. Very simple. I just take the center and I go 2 in each direction. If I want to find my foci, it's a little trickier. I have to go square root of 20. Square root of 20 is, again, it's about 4 point something. So if I go out 4 point something units, I have a focus there. So my foci, I really start at negative 1, and I'm adding the square root of 20, whatever that is, but I'm still at a value of 3. And then I'll subtract it the same way, and I'll get my foci. Now the foci are really not part of the graph. They're just the nice points that really the hyperbola is determined by. The last thing I have to do is really find my asymptotes. Well, the asymptotes for one that is going to be going up and down, or left and right, pardon me, transverse on the x is, remember, b over a. So it's y equals plus or minus b over a. So that's 4 over 2 times x. Now, this is not going to be the actual asymptote because instead of x, it's going to be x plus 1, which is just what we had earlier. And when I look at the y, it's y minus 3, because again, that's how it was shifted. So instead of x and y, I have the things that were in the original equation just as well. But the cool thing is, the only thing I really care about in this asymptote is this slope, which is 2, 4 over 2, which is 2. Because if I want to graph it, I can go up 2 over 1 and get an asymptote there, because I just start at the center. These shifts just mean you start the asymptotes at the center. And then I could go down 2 over 2, and I get it looking like this. So I'll simply go through my vertices close to those asymptotes to get my hyperbola. All right, so if I look at Desmos, very similar, very similar. You can kind of see where the center is at -1, 3. In between those two, there's a vertice, there's a vertice. And again, our asymptotes would kind of fill the gap here. Okay, so that's all for hyperbolas. Definitely the hardest kind of section because it's the most bizarre. Very few shapes take the shape of a hyperbola. But in advanced math, a really important one. So if you have questions, please let us know.